That's a specific question. That's not a general question. So the Barbies are here to help us understand mathematics. You know, and for the record, not all of them have been itemized. Some of them were actually purchased using my own funds. So I always have to be careful giving this lecture as it is recorded, and some of you may have my wife's email address. So we're going to discuss the marriage problem today. There's a lot of good mathematics behind the marriage problem. It's sometimes called the secretary problem. There's a lot of different ways of formulating it. I'm going to use the traditional format of the problem. So the traditional format of the problem is you have one person who looks at a chain of people one at a time. And you have to make the decision as you see each person one at a time, do I want to marry them, hire them, whatever, or not? Okay, so let's say, to try to get rid of all issues that I could get into trouble with, we will have a cow who is trying to choose a worker, okay? And or trying to choose a student to come to Williams College. All right, we'll do it as someone to come to study at Williams College. So we do not know ahead of time who is going to be applying. I will assume we know how many people are applying. All right, so in this case, you can count how many Barbies, Star Trek figures, and cows there are, and that is our number. So we know that, but we do not know ahead of time how good each candidate is. We don't know what the distribution looks like. And we see each person one at a time, and we can score them as we see them. And then we have to decide at that moment, do we want the person or not? And so let's say this is our first contestant. We see her, and we decide she's lacking. Gone. No chance of her coming back. So no hookups, relapses, whatever you want. No second chances. Once someone says no, all right, Snow White now comes. And again, Snow White is found lacking and gone. Okay? So we keep going like this one at a time. All right? Who's this guy? Christoph. Sometimes he is called Hans in the movie, but that was a mistake. All right? Right. This is Christoph. We look at Christoph. Christoph's also lacking. Gone. All right? And now, after we look at a couple of people, now maybe we come to, I think, is this one of the Ilsas? No, this is Cinderella. Okay, Cinderella. And so we see Cinderella, and we decide, yeah, we're gonna. And so Cinderella gets into Williams. Okay? Let's see if she can stay up over here. All right. Yeah. I was going to say, I should have started with Christoph. There we go. Okay. So we will keep Cinderella. All right. And now we don't look at any of the rest of the people. And the people we've looked at and thrown away, we do not have the ability to take them again. What do you think our objective is? To get the best person. Okay? Then there's a lot of different ways you can score what goes on. If you have the second best person, is that a failure? For this purpose, it is a failure. All right, this is maybe where the Disney imagery of your prince, princess, whatever, and true love could be useful. If it's not true love, it doesn't matter. It's a failure. So getting the second best person and the worst person is equivalent. Okay, in the real world, that's probably not the case, and you would probably want to have additional mathematics. There's a great TV show years ago called Mad TV. Anybody ever watch Mad TV? Ever see the Lowered Expectations? It's like the last resort dating service. As you start going through the list of people, what might happen as you get closer and closer to the end? Expectations get lower. You start to realize this might be a good time to settle. All right? We will consider for this class that if you have the second best or the worst person, it is equally bad. It is only a success if you end with the best person. So you're going to see the people one at a time. And you need to decide as you see them, do I take them or do I throw them away? And if you throw them away, you cannot get them back. So we want to come up with a strategy to find the greatest chance of ending up with the best person. And again, there is no penalty here for having the worst over having the second best. If anybody's looking for really good colloquium talk, especially if you can get Valentine's Day in the spring, this is a great topic, and I've had a student who's done that before. What do you think your strategy might be to find the best person? Yes?
You could so if you're looking at the line of people, you could look at the first person and then go down the line and compare everyone else to that first person.
Can't do that.
You
You see each person one at a time, and then as soon as you see them, you either say yay or nay. And let's say poor Cinderella, we'll change our mind. We decided not to have her go to Williams after all. Life's not worth living. She kills herself. There's no chance that she will come to Williams now. This is the original dark Disney movies from like the 1930s. Okay? And so now the next person up, now we have to decide, do we want Data? Yeah, I mean, I would go with Data. I think Data is a really strong candidate for Williams. He may not be as well-rounded, but we can always, increase his data file. Yeah. Just give him the history chip. Okay? So we see each person one at a time. And once we say no, we can't go back. So you cannot compare everybody with the first person. So here's our line of people. If Kayla were here, she would draw better. Yes? Yes. So I am assuming we know that there are n people, and we'll know the value of n. Now, a great problem to do is not to know what n is. And maybe n has a different distribution. Maybe n is uniform. Maybe n is exponential.
Do we know the mean
Nope. Nope. We just see each person, and then we can give each person a score, and then we can compare that person to the people we've already seen. So if I see person 1, maybe I give them a 31, a 42, an 18. Oh, that's a horrible 18. An 18. And I can give them all scores, but I can only give scores to people as I see. And if I've given this person an 18, I've now lost access to this person and this person. Yes? I mean, if you want to pretend there's a maximum score, sure. But it doesn't really matter because we're really comparing them relative to each other. And so we have as much freedom. Yes?
Well, you should never accept somebody who's scored lower than anybody else before them.
Well, but again, it's once we are done with them.
We're only trying to. It only matters if we get the best. If we've already, if somebody's ahead of them.
Good. So if it only matters if we get the best, as soon as we see that this person, let's do it at 42 this time. If this person is, and now we say we don't want to take this person. If this person was a 41, we know we have no chance of winning if we take them. They can't be the best. So we can remember their scores. So we would never want to start with the 41. Can somebody give me a strategy where you will get the best person 1 out of n times? Take the first person. Somebody give me another strategy where you get the best person 1 out of n times. Take the last person. Give me another strategy. Take the second one. So if you want a strategy that gives you the best person 1 out of n times, just specify I'm always going to take whoever's in slot 3 or 4 or 5. Okay. So we have a lower bound. The worst we can do is a strategy that will give us a chance of 1 over n. What's the best we can do? Theoretically. Yes?
What if you took like the...
No, I'm just asking right now. Theoretically, what's the best we could do? Yes?
You always get the best person.
We always get the best person. So the theoretical max is 100% of the time we end up with the best person. My goal is to help you get to that theoretical max. I do have a former probability student who swore to me that this is how he would choose his spouse. This was 6 years ago. He's still single. So take that with a grain of salt. Yes. But, again, he's still alive. There's a chance. Okay? So we have somewhere between 1 over n and 100%. Now, the interesting thing is, as you let n get very, very large, what does 1 over n go to? 0. So in the limit, if you just always take the first, last, or fifth person, in the limit, you get the best person 0% of the time. So is it possible to have a strategy that does significantly better than that? Yes.
What if, as you're taking the first few people, you calculate the mean and the variance, and then as you're going along, once you find someone that's like 3 standard deviations above the mean?
Okay, so that's one possibility. The problem is that's assuming we have some way of knowing maybe kind of distribution that's coming from. You're on the right track. So what you were saying is look at a subset of people and calculate something related to this subset. So the factor we're going to have to decide is how many people do we look at? Let's look at the first k people. 1, 2, 3, ... k. Now we could look at mean, we could look at variance, but we know something, and it was already remarked. It is a complete failure if we do not end up with the best person. What should we look at? Not the mean, not the variance. Maximum. Look at the maximum score. Right? Because we really don't care about the mean, we don't really care about the variance. We just care who is the best. And so let's say, she's dead, but we do remember Cinderella. For a long time, she was the leading candidate for admission to Williams. We may be regretting now that we threw her away. I know this is not how Elsa stopped talking from my previous class. We remember what the best score is. What do you think our decision rule should be now as we look at the remaining people?
If the score of any person from k plus 1 to n has a score greater than that of the max score of the first k people, take that person.
Good. So take first better than the max of the first k. Because we know if we take somebody whose score is lower than the best we've seen, clearly we lose. The only chance we have of winning is taking somebody who's better. Let's take the first one who's better. Now, of course, we could take the second one that's better, or the third one. And so the question is, what is the best strategy? And I'll let you investigate what would happen if you took the second person who was better. What happens if none of them is better? You lose. Right? If you want, you can say you choose the last person and you settle with them, and it's, just so you have someone, but you won't be happy. How often do you think we're going to get the best person? Now, we know if we choose the first person, we'll write 1 over n times. And in the limit, that's 0. Do you think that our answer, the probability that we get the best person, do you think it's a positive probability? Do you think it's like 1 over n, maybe better 1 over square root of n? How likely do you think it is, as n gets large, that we end up with the best person? Do you think we even have a 5% chance? Or do you think in the limit it's 0%, but maybe a higher 0 than 1 over n? So I deliberately did not want you to be aware that we were going to do this today so that it would be a surprise. It's very tough to estimate these probabilities. And humans, we just do not have a lot of good experience in estimating. The other question, of course, for this problem is there's something else we need to determine. What else do we need to determine? What k should be. So what we want to do is for each choice of k, we want to calculate what's the probability we end up with the best person. And then we'll maximize this over k. What I love, and I really did not prepare today's lecture because I had a 5-hour school committee meeting last night, is I believe this will allow us to review almost all of Calc 1 with some nice twists. There's a lot of really good stuff in this problem. So the goal is for fixed k, what's the best we do? So what is probability we win if choose a specific value of k for gathering purposes? So, if you are trying to do this in practice, do not tell the people you're dating that this is merely an exploratory phase and that you have no intent of having a serious relationship. You're just trying to get some data. Okay? What's the probability we automatically lose? There's got to be some easy cases. Can somebody give me a lower bound for the probability we lose? Yes? K over n. So if the best person is in the first k, you're screwed. There's nothing you can do. So always lose if best in first k. When do you win? And again, this may not be the best way to analyze it, but there's at least a simple case where you know you'll win.
If the second best person is in the first K,
Good. Always win if second best in the first K, but best isn't. So in that case, you'll always win. So then the question becomes, can we come up with a nice situation, a nice analysis? Let's assume the best person is located at slot M. So this is the best person. Okay? So we want to know, if we look at the first K, what is the probability that this person is the first person we see better than the best person in the first K? What would it mean for them to be better than everybody in the first K, and we haven't chosen anybody from K plus 1 to M minus 1? What would that mean?
He's better than all the people who came before him.
So first of all, M has to be better than all the people before them. And since we've assumed that M is the best person, M will be better than all the people before them. So that's half the problem. What's the other half?
That there can be no one from K plus 1 to M who has a score greater than the max score.
So the maximum score here has to be better than all these people over here. Another way of saying this is, if we look at the first M minus 1 people, where must the best of the first M minus 1 be? In the first K. So we win if the best in the first M minus 1 is in the first K. And this is where you have to really think about, how do you want to do the algebra? Do we want to have this person located at M, or do we want to have the best person located at M plus 1? You can do it both ways. It doesn't really make a huge difference. It will change the algebra a little bit. This is where years of experience, not in dating, but in mathematics, will help. Any thoughts here? I will let the class decide. Do you want M, or do you want the best at M minus 1? M, okay. I like M right now because I've already written M on the board, and this way I don't have to erase. So we'll say that the best is at M, and we'll see later if it really makes much of a difference for the algebra. So we want to calculate what is the probability we win given that the best person is at location M. What kind of probability is this? Conditional. We've got the word given, right? So we want to calculate, so the probability of a win is going to be the sum, M goes from 1 to N, of the probability of a win given the best is at M times the probability best at M. So what's the probability the best person's at M? 1 over N. We're assuming everybody is equally likely to be in each spot. Where do I really need to start the sum? So right now I've got the sum going from 1 to N. So where should I start the sum? What should be the smallest value of M I look at? K plus 1. Because what's the probability we win given the best is at M? If M is less than K, 0. Right? Because we have to look at the first K. So all of those are going to be 0. So we might as well have M go from K plus 1 to N. Now what's the probability we win? So now the best is at M, which is beyond K. And what we want is we want the best of the first M minus 1 to be in the first K. What's the probability that the best of the first M minus 1 is in the first K? K over M minus 1. There's M minus 1 slots. The best person of the first M minus 1 is equally likely to be in all the slots. Therefore, the probability that they're in the first k slots is I have k slots where they could be, and I win, and I have n minus 1 possible slots where they could be, so the probability that they're in one of the slots I need is k over m minus 1. And then the probability that the best is at m is just 1 over n. Now you can begin to see a little bit why we might want the sum to go from, why we might want an m minus 1 rather than an m, but it won't be too bad. We can always shift things in a little bit. The k over n is easy to handle. We can just pull that out. And so we have a k over n, and then we have a sum. M goes from k plus 1 to n of 1 over m minus 1. Okay? So here is the probability that we win as a function of n and k. We've done the sum over m, so there's no longer an m here. And now the question is, well, we can compute this, and then we just find the value of k as a function of n that optimizes this. This may not be practical for you, but let's look at the limit as n gets very, very large. Okay, so we'll assume we have a huge number of people that either we're interviewing for the job, trying to decide if we want to admit them to Williams, if we want to marry them. Okay, normally in a Disney movie it's about 2, maybe 3, for the candidates, but we'll assume n is large and try to estimate what's going on. If n is large, what does this look like over here? Well, what kind of series does this look like? We've seen it, we saw it on Monday. I'm sorry? Geometric would be each one would be a fixed multiple of the previous. Harmonic. So this is going to be, which in a sense we're trying to find something harmonious, right? So we have k over n, we would have m goes from k plus 1 to n, so we would have 1 over k plus 1 over k plus 1 plus 1 over n minus 1. So it's like a harmonic sum, but we're missing the 1 plus 2 plus the 1 plus a half plus a third plus a fourth plus dot to dot plus 1 over k. So if you want, we could actually write this as a difference of two harmonic sums. So this would be the same as k over n, and then it would be the harmonic sum going up to n minus 1 minus the harmonic sum going up to k minus 1. So what I'm doing is I'm doing one of my favorite things in mathematics. I'm doing nothing. I'm adding 0. How am I adding 0? I'm adding 1 plus 1 half plus 1 third plus 1 over k minus 1, and then I'm subtracting 1 plus 1 half plus 1 third plus 1 over k minus 1. And the harmonic sum is just the sum of the first n minus 1 reciprocals. Now, we have lots of different estimates. There's actually a constant term, but I don't have to worry about the constant term in my analysis because it's going to cancel. So you should have seen in calculus that if you have 1 plus 1 half plus 1 over L, this is approximately the log of L. There is a constant, but that constant is not going to matter because it will cancel. The other term is going to be like a 1 over L. So just as a rough approximation, this is going to be k over n, and then we'll have the log of n minus 1 minus the log of k minus 1. So this is approximately k over n, the log of n minus 1 over k minus 1. The log of a difference is the quotient of the logs. How do you want to approximate the log of n minus 1 over k minus 1? Just to make the analysis nicer. It's approximately n over, yeah. So just call it k over n, the log of n over k. And so that's the probability we end up with the best person. And then different values of k will give us different answers. What's fascinating is this is already enough to see that we can do a positive percent. If we take k to be, say, n halves, this would be a 1 half over here, and then we would have a log of 2. The log of 2 base e is about 0.69. So we'd have about 70 times 50, about 35%. So just as a quick rough estimate, that gives us about 35% if we take n halves. That's kind of excessive. We're looking at the first n over 2 people, throwing them all away, but using that to get a really good sample of the space. And that's enough to have an extremely high probability, not a certainty, but a really high probability that we end up with the best case. To me, this result is absolutely shocking. That you can get a positive probability, and we've just done a quick sketch. Here's essentially 35%. With a little bit of work, I can get up to a little bit over 36%. It's not a huge increase, but this is eternal happiness. It's worth doing a little bit extra math. Plus, it allows me to review almost all of Calc 1 in 10 minutes. Okay? What do we want to do? So we've just shown the probability when, if, look at k is approximately equal to k over n, the log of n over k. So what do we want to do now? We want to maximize. What would you love to use to maximize things? I'm sorry? Derivatives. Are we allowed to use derivatives here? Really? So you can look at a third of a person? Are you allowed to continuously variance? So I guess I can do this with the camera, and maybe we can have, oh no, the camera's turning with me, so. Oh, okay, there we go. So I can have slowly coming in continuously, right? Are you allowed to look at part of a person? No.
Couldn't you find the fraction that's the best and then just look at the two numbers close?
So what if my function is the following? Here's 14, 15, 16, 17, 18. And maybe I go up, then go down, then go up, and then go. And so if my function has enormous fluctuations, I don't know that my integer max is near my real max. So whenever you have to optimize an integer valued function, things are hard. What we will hope is that the integer max is near the real max. And so what we'll do is we will first look at the real valued function and then see that in fact the integer max is, as you suggest, going to be either right before or right after. So let's look at the function f of x equals the log of x over x. Okay? So I'm letting x be n over k. So how do we find the max? Yes? Did I do this in this class, or was it operations research? I think it was operations research, so I haven't done the lesson in this. All right? Tell me where I'm traveling my fastest. Okay? Yes. It's not enough to just look. And this is why they couldn't use me to start one of the games when the Patriots' second string or third string quarterbacks were injured, because I had done this in operations research and I hurt my throwing arm. Yes. That was the reason. It's not enough to check critical points. What else must you check?
You need to check if it's a max and not a min.
We need to check max and min, but it's not enough to just check critical points. What else must you do? Endpoints, right? Now, what would be the endpoints here? We could take k equals 1, and it's going to be, we'll see very quickly, okay, if k equals 1, this is a log n over n. It's a little bit better than 1 over n. So it's at least an improvement. But if we take k equals 1, it's bad. So k equals 1, bad. It's approximately log n over n. What if k equals n? It's even worse. It's damn bad. It's about 1 over n. Because the only way it works is, I think, essentially, maybe we're choosing the very last person. So the endpoints are not going to be where we are going to get the best choice. It's going to be for some intermediate value of k. And in fact, we just even showed if we take k to be n halves, we're getting around 35%. Yes?
If k equals n, doesn't the log just equal 0?
Right, so I guess technically maybe I'm doing k equals n minus 1. So yeah, I mean, depending on how you want to view things, it's either 0 or 1 over n. It's bad. It's not even close to what we're getting when we take k to be n halves. So it will be the critical point, which is where it is. Most of the time, it's the critical point and it's not the endpoints. Almost surely the following is not a true story, but it's amusing and I smile when I tell it, so I will tell it. The story is they were trying to build, the stealth bomber and the stealth fighter. What is your objective if you're building one of these? Stealth, okay. And that means?
Minimize surface area.
Well, okay, not necessarily minimize surface area. You want to minimize?
Its detectability.
You want to minimize its detectability. So the story, which is almost surely false, is that they didn't check to see if they were at a maximum or a minimum, and they actually built the I'm here plane. Probably not the case. If so, things coming off at strange angles and loud sirens blaring might have given away that you're not doing a good job maximizing and optimizing. But it's just funny to think, if you don't check, you might actually be at the wrong point. There's also local maxima versus global maxima. You have to really worry about stuff like this. We will be in a very good shape here. All right, how do we take the derivative of log x over x? So there's a lot of different ways we could do this. We could try doing it with the quotient rule. The other thing we could do is we could write this as x. We'll do it with the quotient rule. All right. So f prime of x is going to be our quotient rule. So the derivative of log is 1 over x times x minus x. Am I doing this right? Okay, yes. So the derivative of log is 1 over x minus x minus log of x times the derivative of x, which is just 1 over x squared. And so we get f prime of x is equal to 1 minus log of x over x squared. Okay? So where's the critical point? Critical point is x equals e. Right? The log of e is just 1. And so if x equals e, that means n over k is approximately e, so k is about n divided by e. And 1 over e is approximately, I think, 36.78. Let's do a bunch of zeros. 36.7879%. So what this is saying is you look at the first roughly 37% of the people, don't tell them that they have no chance, and then you use that to make your guess for how you should look at the rest. What's the probability you win? Well, we now have n over k is about 1 over e. And so, I'm sorry, n over k is e. So we have 1 over e times the log of e. The log of e is. So we win with this percentage. So about 37% of the time, we will find the best person. Now what you could do is you could ask a bunch of related questions. What might be a nice related question? What would be a good related question to this?
What if the probability you get the second best?
Yeah, what's the probability you get the first or the second best person? How high would that be? If you do that, I think it's almost 50%. And so then if you consider the second best person is not that bad, and then you could ask a whole slew of questions. I encourage you to do this. It could be very useful later in your life. Okay? So 37% of the chance of the time. Well, unfortunately, this is only if we can do things continuously. All right, what if we do things discretely? Well, let's go back to calculus, and let's look at how we plot functions. So in the old days, we did not have calculators and computers. We did things by hand. So here's the x-axis, and here's f prime. So here is 0, here's infinity, and where's the critical point? E. What can you tell me about the derivative at E? 0. What can you tell me about the derivative before E? So when x is less than E, what can you tell me about the derivative? It's positive. What can you tell me about the derivative after E? Negative. So we know the shape of the function. If the first derivative is positive, the function's increasing. I'm just doing this to get my steps for the day. If the first derivative is negative, what about the function? It's decreasing. So I know roughly it looks the following. Something like this. The actual shape I don't know, but I know it's increasing up to E and then decreasing from that point onward. So now we can go back to the suggestion from earlier. Find the real maximum and then check immediately to the left and the right as to which is the best. So the best integer candidate is going to be one of those two values. And I guess technically we're really looking at, I think, n over E. Or maybe we're looking for the value, something like that, in terms of just what label you want to use. So here, if we're doing it for x, x is going to be E. So I guess here I'm just plotting it as x, and then we'll translate from x to k. All right, so this tells us that the best value, if we want to do things for k, we can just rescale. So this is the marriage problem. This is the secretary problem. It reviews a lot of the great things we've been doing throughout the semester. It reviews conditional probability. It reviews breaking a complicated event into a bunch of simpler events. What's the probability we win? Well, let's write it as a function of where the best person is. Is the best person in slot 1, slot 2, slot 3, slot 4? When you have a complicated problem, if you can break it up into a lot of simpler problems, this is often progress. Then we have to do the analysis. The hardest part was figuring out what's the probability we win if the best person is at M. Well, what's nice is it's not too bad. It just comes down to where is the best person of the first M minus 1. And if that's in the first K, just these very simple arguments. So it is very easy to overanalyze problems. This happened on the exam. This is why Cam and Kayla were able to get the Skynet problem, is they have not taken all this advanced mathematics, and they just looked at things a little bit simpler. Okay? Then we come down to using the calculus. And how do we find maximum minima? We look for critical points, and we remember the endpoints. All right, fortunately, Brady is back, so I don't have to worry that I'm now questionable to start this week. Okay? Check the endpoints. Most of the time, it's not going to be the endpoints, but you have to be careful. Typically, it's hard to pass from a real max to an integer max, but if you're in a very nice situation like this, we will be able to do this. Okay, any questions about the marriage problem? All right, I will make the offer I've made in the past. I will give you extra credit if you use this to choose your spouse. I do not recommend going for that extra credit. So there's a lot of unreasonable things in the marriage problem. One of the biggest is knowing ahead of time exactly how many candidates there are. For some things, you might actually have something like that. You might have a job, you might have a period of time where you are accepting applications. And then you start just reading applications, and after a while you realize, we've got a lot of really good people. These people are all about the same. I'll take this one. And I'm not going to spend my time. And I'm going to be so close to the best, it's really not worth spending the additional time to find who is actually the best, especially if I'm not that confident about my ability to make these small distinctions. Just because I assign a number to something doesn't mean that number is accurate. All right. So what I want to now do is I want to now switch to Poisson random variables. Okay. So this is going to be a nice discrete distribution. We will have the probability of n is going to be lambda to the n, e to the minus n, divided by n factorial, n 0, 1, 2, all the way to infinity. Okay? I want this to be a probability distribution. What do I want to assume about lambda? So lambda is going to be my parameter. What should I assume about lambda?
It's positive?
Probably positive. If you want, I am happy to rumble as to whether or not lambda equals 0 is acceptable. If lambda equals 0, then all these probabilities will be 0 except when n equals 0, and then you have 0 to the 0, and I'm willing to be convinced that 0 to the 0 is 1. I'm also happy to just say let lambda just be greater than 0 and not really worry about that. But if lambda equals 0, this is in some sense a spike. Think of it as the Mobius coin. With probability 1, it comes up as this quantity. Okay. If lambda were negative, then this would not be a probability. It would alternate between positive and negative values. So if we assume this, it's clearly going to be greater than 0. It'll be positive. We need to make sure that it sums to 1. So the sum, n goes from 0 to infinity, of lambda to the n, e to the minus n over n factorial, is just e to the minus n, and then the sum, n goes from 0, typo, bad typo. That should be an e to the negative lambda. Should be e to the minus lambda, lambda to the n over n factorial. Well, what's the sum of lambda to the n over n factorial? E to the lambda. So we get e to the minus lambda times e to the lambda, which is just 1. So it is a probability distribution. And this is how I quickly realized I must have made a typo by putting an e to the minus n. Is the e to the minus lambda, this is essentially our normalization constant. All right, so this is a nice probability distribution. What should we ask? What's the mean? No. We may not have time to get into everything, but I always like to tell stories. Does lambda have units? When we had the exponential, we had e to the negative x over lambda. Does lambda have units? No, lambda is unitless. If lambda had units, these things would all be of different units. You'd have maybe meters, meters squared, meters cubed, meters to the fourth. Lambda is unitless. Think of lambda as the number of events. So we often use the Poisson process to model the number of, say, accidents at an intersection. And the number of accidents is going to be a physical number. It's not going to be, we have 15 cubic meters of accidents. We have 15 accidents. What that means is it's much harder to analyze Poisson random variables than others because you lose intuition. When you have units, you can quickly look at something and get a sense of how the answer should be as a function of the parameters. So if I were to give you as an aside, and I'll erase this quickly, let's say I want to integrate x to the fourth e to the minus ax dx. If I make x meters, I would want to have a as, what would the units of a be? 1 over meters. I would want this exponential to be unitless. Because when I exponentiate this, I'll have 1 plus ax squared over 2 factorial. I'll have the minus signs. So unless a has the opposite, the reciprocal units of x, these will all have different quantities. So if x is meters, a is 1 over meters. So what would be the units of this integral? Meters to the fifth. So I know it has to look like 1 over a to the fifth. Without doing any analysis, it's got to look like that. That's the only way I can get a meters to the fifth. Years ago, when I was taking complex analysis at Yale, we needed a bound, and I raised my hand and I said, Professor, your answer is wrong. The units don't work. I was, what? Oh, I'm sorry, I'm speaking physics. The degree of homogeneity in the parameters is wrong. Oh, yes, you're right. And so the physicists are much nicer. They use words like units. The mathematicians often talk about how it varies with the parameters. But I really like to think of it in terms of units. You can quickly look at this, and you can see it's got to be a 1 over a to the fifth. Because lambda is unitless, I can't quickly look at this and see how the mean and the variance should be as functions of lambda. So we want to calculate the mean. That's the first question you ask when you meet a random variable. After you get to know the random variable a little bit better, what do you ask? The variance. And then this could actually lead into the marriage problem as to, is this the random variable you want to spend the rest of your life with? All right, so we want to calculate the expected value of the mean. This is just going to be the sum, n goes from 0 to infinity, of n, lambda to the n, e to the minus lambda over n factorial. We could use differentiating identities to solve this. How else could we solve this? Yes?
You know, n divided by n factorial is 1 divided by n minus 1 factorial.
Yeah. So we could actually just do some algebra rearrangements. Now, we have to be a little bit careful. We don't want to take negative 1 factorial. Right? Does anybody know what negative 1 factorial is? No. Negative 1 factorial is actually infinity. So if you have a negative 1 factorial down below, you'll be fine. Later on in the semester, we will learn that negative 1/2 factorial is the square root of pi. We'll see that later. That's probably my favorite factorial. Obviously, it loses combinatorial meaning. So we can change this, since we're calculating the mean, to start at 1. We can pull out a lambda. And if we pull out a lambda, we have lambda. The sum n goes from 1 to infinity of lambda to the n minus 1. We can even pull out an e to the minus lambda over n minus 1 factorial. Well, what's lambda to the n minus 1 over n minus 1 factorial? If you want, I can shift the sum and go from 0 to infinity, lambda to the m over m factorial. What will this be? It'll be e to the lambda, cancels the e to the minus lambda, and we get that the mean of a Poisson random variable with parameter lambda is lambda. Good. I mean, that seems like a good choice then of what we're calling our parameter. All right, now we want to calculate the variance. So when we can calculate the variance, that's the expected value of x squared minus the square of the expected value. Well, this part is no problem. This is just lambda squared. So we need to calculate this part. So this would be the sum, and I'll go from 1 to infinity of n squared, lambda to the n, e to the minus lambda over n times n minus 1 factorial. How could we handle this? Well, this is highly suggesting let's cancel an n. Right. We could do this by differentiating identities. If we cancel an n, I'll pull out a lambda, e to the minus lambda. I'll have a sum, and it goes from 1 to infinity. And I'll have an n, lambda to the n, over n minus 1 factorial. Sadly, this is not something we immediately know. There is a trick. So there's two things you can do in mathematics. You can add 0, and you can multiply by 1. And one of my professors at Yale said the log of 1 is 0, so there's really only one thing you can do in mathematics. You can do nothing. There's a couple of different ways you can do nothing. Does anybody know a good way to write n by adding 0 to it? And if you look at this expression, there's a hint as to what you would like. You don't want an n upstairs. What do you want upstairs? Yes? Yeah, so this would be the same as lambda e to the minus lambda. The sum n goes from 1 to infinity of n minus 1, lambda to the n, over n minus 1, n minus 2 factorial. Am I allowed to just subtract 1? No. So what do I have to do? Add 1. So I'll now have two terms. Right? The first term will be an n minus 1 over n minus 1. So we'll have a lambda e to the minus lambda, and then we'll have a sum, n goes from 1 to infinity, of n minus 1, lambda to the n, over n minus 1, n minus 2 factorial. Where should I start this sum? Running out of time. Where should I start the sum?
0.
Not 0. 2. Because when n equals 1, I have 0 upstairs. So I might as well start the sum at 2. And then the next piece, I have a sum, I have 1. So it would have the sum, n goes from 1 to infinity, of lambda to the n over n minus 1 factorial. I'll pull out a lambda and have that as lambda to the n minus 1. All right, so now I have lambda e to the minus lambda. This piece over here, the n minus 1's cancel. What do I want to pull out of this? I don't want lambda to the n. I want to pull out 2 lambdas, a lambda squared. So I'll do lambda squared n minus 2. And I should get something like lambda squared. And then the sum of that will just be e to the lambda. And then this piece I'll have lambda. And there will also be an e to the lambda. So we're almost done. So these cancel. And I think, if we've done it right. Oh, actually, sorry. I did not pull out a lambda this time. I was doing that from the last time. I haven't pulled out this lambda. I apologize. There's no lambda there. So I get lambda squared plus lambda is the expected value of x squared. And then we will end with the variance will then be lambda squared plus lambda minus lambda squared, which is lambda. And this is really bad. I mean, it's the answer, so we have no choice. This is what it is. But the problem is the variance actually has the same units, well, not the same units, the same power of lambda as the mean. And that's because lambda is unitless. If it had units, you would not expect the mean and the variance to have the same units. What quantity has the same units as the mean? The standard deviation. But because the Poisson is such a strange distribution, the variance and the mean are the ones that have the same parameter dependence. All right, this is a good place to stop.